Good afternoon. I would like to welcome Gardson Githu. He's a professional engineer. He's a senior mechanical engineer and consultant at EYP Mission Critical Facilities. Gardson's experience focuses on the design and analysis of HVAC systems for commercial, industrial, and data center infrastructure facilities. His experience includes new facilities design, retrofit design, and mechanical system analysis. He holds a bachelor's degree of science in mechanical engineering from California State University Los Angeles and a master's of science degree in mechanical engineering with Themo-fluids option from California State University Northridge. He's a team member of the recently launched EYP Mission Critical Facilities and I3 Solution Group Sustainability Initiative to offer practical roadmap towards a carbon net zero or near net zero data center by 2030. So welcome, Gardson. Thank you for joining this podcast. And we are looking forward to have a great conversation today.
Thank you for having me, David. Good to be here.
Sure, Gardson. Thank you again. And so where do we start with this? How did you start with this initiative? What prompted you to start using CFD analysis? So not only in the race floor area, but outside, and what prompted you to start working on this aspect?
So what led us to start using the computational fluid dynamics was the need to understand the flow phenomenon of the how the air patterns and the flow rates and the behavior of the air in the data center space. Like you mentioned, before 17 years ago, the only available softwares would only do the analysis for the race floor, place. Now, over the years, the software developers, they have improved in the software that today we not only doing and performing CFD analysis, which is computational fluid dynamics analysis for the race floor applications, but also above the race floor, and also now today we are able to do and perform analysis outside the data center. So now we have two sets of modeling we are doing, which is the internal models, what we call internal models, which is inside the data center, and the external model, which is outside the data center. And it's that external model that led me to writing that blog, just to emphasize the importance of doing computational fluid dynamics outside the data center, which has been led by increased load densities in some of the data centers we are designing nowadays. And we are finding that we really need to pay attention also, not only what's happening inside the data center, but also what's happening outside the data center, because it has an impact on the performance of the data center.
So, but there's also something in between. So it's inside the data center, but within the data center, you have the race floor. Mm-hmm. That's the inside of the official part of the IT. But then you also have inside of the data center something new, because usually it was only race floor. So it's outside of the building, inside of the race floor, and also the mechanical equipment.
Yeah, all of that. The chillers, all of the above. Look at it this way. Before, the softwares which were available could only do, like I said, under the floor to see what's the air distribution happening underneath the raised floor.
Right.
Now, most of the data centers too, they have moved to not using the raised floor. Mm-hmm. So there's no more raised floor. That means the equipment we are using are not configured for raised floor application anymore.
Okay.
That's one part. Then the other part is the equipment, like you just mentioned. we find that even the equipment like the UPSs, the PDUs, sometimes they are located within the space of the data center or outside the data center space, and also they are factoring into the heat gain within the whole overall data center setup. Yes.
Okay. So you wrote a blog. It seems that there's a great replies from different people. In fact, you almost reach within the last 2 weeks. I almost reached 500 viewers of that blog, so you're getting a lot of reaction, which is good news. After the blog you publish, questions came asking what is CFD analysis. So what is CFD analysis?
So computational fluid dynamics is a branch of science, and to be more specific, a branch of fluid mechanics. And what it does is it utilizes numerical methods to solve for fluid flow problems. It's not a new thing. It's not a new tool. It's something which has been there for a long time. Started with aerospace industry, the automotive industries, they use it. And so many sectors of our economy, they use CFD analysis in engineering calculation. But now for us in data center industry, we use it to understand the flow patterns within the space. Now our working fluid, in this case, it's air. So, and we use computational fluid dynamics to predict the patterns so that we can solve issues that might arise inside the data center space.
How does EYP use CFD analysis?
So at EYP, we use CFD analysis for a couple of things. One is we use it to validate our design.
Right.
The next one is to verify our design that it will work as required. Mm-hmm. And then lastly, we use it as a design tool.
Okay.
We use CFD as a complement to other conventional engineering analysis. So it's not just the only tool that we depend on. So we'll do all the engineering that's required, and do all the layouts that are required. And then we look back and say, how can we verify, this design which we are proposing to our clients that it will work. So right. One of the tools we use is computational fluid dynamics.
Now, is it one design or is it multiple designs, multiple modeling?
It depends how many models we want to do. Let's give you a good example. When we design a data center, we have, the maximum load that can be handled in that data center. So we'll probably start with that model, which is the maximum load you can have in the data center space. Then after that, we'll do multiple scenarios, like, okay, the client might mention, for the first 3 years, I'm only gonna load up that data center 50%. Mm-hmm. How does that look? How do you automate the system so that I'm not using too much energy? I'm just using what I need for that scenario. The other scenario we do is the failure mode scenarios, right? So in all data centers, there's the redundancy equipment. Right. So the question will be, if I had like a good example would be, I have 10 cooling units in the space and 2 of them are redundant. So you would like to see, if I fail those 2 units, would the remaining 8 units be able to handle the load inside the data center? Right. So in one model, it might generate so many other scenarios as you continue, and that will always comes from the clients, the end users want to know, then we can do that simulations for them. The other one we do is what we call transient analysis, which is, if you think of a data center and there's a power failure, And all the IT equipment, to the most part, they will be on the UPS. So they don't see interruption of the power during the power failure scenario, let's say in case of a power failure from the utilities. And the data centers are always set up to have backup standby generators.
Yeah.
So the UPSs, the IT equipment will continue doing what they are doing, but because there's an interruption of power when you switch from the utility to the backup, the mechanical equipment sometimes will drop, which means is they stop running because they are not powered for maybe a small duration of seconds. It could be minutes, depending on how the system is configured. And what we do is with the transient analysis, still from the CFD analysis, is to see during that transition, what's the temperature rise inside the data hall? Is that something that can be sustained? Will the equipment, the IT equipment, start receiving inlet air temperature, which is not within the allowable range? And then at that point, then we can make a decision of, it's probably a decision whether do we need to have some of the mechanical equipment on UPS power, or do we need to have a thermal storage, which will help during that transition not to see the temperature rise.
Now, what are the benefits and advantages of CFD analysis?
Well, the benefits of CFD analysis, number one is ability to pull information which you can't get because there's no way to have a setup. You have to have an experiment where you can go get that information, right? Like in a data center, you have to build it and fill it up to get all this information, right? But now with the CFD analysis, it gives us the ability to get that information, which in other words, it will be very difficult to obtain. The other benefit is simulating, like I mentioned, simulating real conditions and multiple scenarios, which essentially will be very difficult to simulate sometimes on a real data center, on a live data center, or even for a data center which is not even built. The fourth benefit is once we get the results, we are able to visualize, give us a good visual understanding of what's going on, and which does not require any engineering training or anything. You just look at the result and you can tell, okay, over here is hot, over here is cold, and make the decision from there. The other thing we do with that, with the CFD, the benefit is the ability to able to optimize a system for energy savings purposes. It's not only for looking into areas where you have problems with the airflow, right? Or you have hotspots in the data center. It's not only that. The other one will be, hey, I'm overcooling some areas in the data center. Why am I overcooling? Do I really need to overcool? Right. When you overcool, it means essentially you're using more energy. So we are able to fine tune, we are able to optimize, and come up with lower PUEs in some of these data centers. Correct.
Now, speaking outside of the raised floor area or the IT area, white space area, if you're not using a white space, then the IT area. Now, when it comes outside, do you use the same principles? I remember years ago, my friend Robert Tozer, who's a former EYP Mission Critical, he did a wonderful presentation that he talked about exergy, negative pressure, bypass flow, recirculation flow. Do you still use the same principles when it comes to outside of the raised floor area?
Yes, it's still the same principle, David. We are still using the same theory. And this is it's very interesting with CFD. CFD it uses simple theory. However, it becomes complicated because of the application. So it's simple theory, and the theory is this: we are trying to solve conservation of mass, momentum, and energy equations in the CFD. That's the theory. It's nothing very complicated. It's just that. But the way we apply, like you just mentioned about recirculations and negative pressure, all that are driven by those analyses, and it's the same inside and outside. It's still the same concept. It's still the same theory.
So you mentioned about what happens inside, which I like that approach. One, saving energy. You're talking about also the transition, which was one of the cases that I remember, which was what happens if in a case of emergency, utility goes down, then you have the generators. But what happens if the generators don't work? So the worst case of the worst case scenario, then what's the reaction? So it's, well, it is important that you shut down completely the servers, and you have, let's say, for instance, 3 minutes or 8 minutes to shut down the servers if the HVAC unit didn't go through, because when you shut down a data center manually, it's better than if it shuts down by itself, because then the continuity plan or disaster recovery plan, it's gonna take much less because you shut it down correctly. It's kind of shutting down a computer versus if the computer shuts down by itself, instead of you shutting it down, it's gonna be much easy to restart the computer. So that happens in that case. Now, outside of the data center, do you use similar principles, energy, or it's only energy conservation?
No, you use the same principles. Yeah, even outside the, you are looking at everything. You're looking at the temperature. You are looking at the velocities. You are looking at the pressure. And yeah, it's still the same principle. It's still the same principle applied outside the data center.
So it's not mainly energy conservation, but it also happens to be, what if some of the, like a cooling tower fails? How's the other cooling towers reacting to it, for instance?
No, there's also energy. There's also element of energy conservation there, David, which is you'll be looking about how many number of equipment are you using.
Okay.
Right. You also be looking at that. The other thing is, let's say you have a lot of recirculations, right? Mm-hmm. Outside the data center. Let's say you have a chiller yard. So you have recirculation. Instead of your chillers sitting in a temperature of 80 degrees, because of the recirculation, they see 120. Well, that means that chiller gonna work harder. Working harder means what? It means more energy. So we try to avoid those scenarios, because that's how you start optimizing even outside to have less energy usage too.
Now, do you apply or do you perform a CFD analysis on all of the projects?
Not necessarily. We do not perform on all the projects because sometimes, let's say you have a client who like a specific model, a specific layout. We have performed the first analysis. Probably they went ahead, they built that first facility, and they engaged a third-party commissioning agent. They came through, they did the commissioning, they tested, and everything compared closely to what the CFD was showing. Now, at that point, if you want to build another hall, another data center, another hall, probably it's not economical to do that. So you don't have to do on all of them. But sometimes the clients will say, okay, I still want you to perform analysis for record and documentation. Yeah.
Okay, interesting. So I'm going to show, I know you put on the blog 3 slides. So I'm going to show 3 images. I'll show the 3 images. So maybe you can tell us a little bit about those images.
Okay, so the one you are showing here, David, it's a typical internal model where you have rows of IT equipment. And in this model, yeah, where you have the cursor, yes, those are the rows of IT equipment. And this model, they utilize hot aisle containment, which is connected to return air plenum above the ceiling. And the air from the hot aisle containment is directed back to the crack galleries. You see the crack? Yeah, those are the crack galleries. And in the crack galleries, that's where you have cooling units, the one in gray color. And in this case, in that crack gallery, this design has also electrical equipment, the PDU, the LED boxes. Those are the PDU, power distribution units, which essentially what's inside is a transformer, right?
Okay.
And through that transformation of power, you know, stepping down or stepping it up, these power heat losses. And as you can see at the bottom, where we have that cloud, the contribution of heat from the PDU into the gallery.
Okay.
But so the cooling units in this case will be sized not only to meet the cooling needs for the IT equipment, but
Right.
also the extra heat rejected by the PDUs into the crack gallery.
Okay.
So they share together. So, and this concept here is what we usually call flooded room concept, flooded cold aisle. You can see the entire room is blue, kind of like light blue, which if you look on the temperature ranged on the left, that's 70. You're looking at 70 degrees Fahrenheit inside the cold aisles of the flooded room, and also inside the hot aisle, the yellow kind of looking. That's the hot aisle.
Yep.
As you expect on that legend there too, you're looking close to 104 degrees Fahrenheit. So we perform this, and this will be now a verification. Yeah, this model probably will work. And I think this is a data center we recently did, completed, and has been also commissioned. And there were no surprises. It came the same way it was designed. Yes.
So the question that I have is, I see 3X. It seems that maybe the units are failing or something.
Yes, that's what the one that we are talking about, the fail case scenario, and I think there are 4. The 2 crack units with X on each side, right?
Yes.
Yeah, that and that. So those ones have been turned off to simulate end condition. That means no redundancy. So, and why we do this is at any given time, there will be need to do something with the crack unit, maybe replace the belts, it fails, anything can happen. So we want to see if that happens, you know, what happened in the room. And in this case, when all the redundant equipments were turned off, the cooling was sufficient. There was enough cooling to the IT equipment.
So one more question on this slide. I noticed you mentioned around 70 degrees, 71 degrees on the blue part. Can you increase that temperature? Why it's 70 degrees and not higher temperature?
Okay, so now that's always a design requirement, David. In this case, this client was looking to maintain 72 inside the flooded cold aisle room. So here the target was 72 degrees. Now, today we have other clients, they want to maintain at 78. Right. And others, they want to maintain at 86 degrees Fahrenheit.
Wow.
So yeah, it's dependent. It's dependent with it depends with the client and what they want to do. Well, the higher the temperature, the more energy savings, the lower the PUE. But it also comes with the risks. What we are trying to do here is to simulate a condition outside the building where you locate heat rejection equipment close to a building So we're trying to understand what's the impact will be. Would there be any air recirculation? And in this case, you can see there was air recirculation, especially on the unit on the right side, where you see the air, hot air coming out of the unit goes up and is blocked by the building wall and bounce back into cooling units intake. Yeah, right there. You see the circular movement right there.
Yes, yes, yes.
Yeah. So with CFD analysis, you're able to visualize this. Like I said, one of the benefits of CFD analysis is to visualize these flow phenomenon. And you don't want to wait until when you do commissioning to find out, wow, we got an issue here.
So what is this green?
That's the outside air.
Okay.
And you can see it's restricted at the wall there because it comes through a louver. No, that side where you are. If you keep going on the other side, on the left side, all the way right there.
Right here.
Yeah, right there. Yeah. So yeah. So the green, the greenish area, that's outside there. 100. I think the target here was 100. Shows there 115. Yeah, 115, 100 degrees Fahrenheit coming through.
So that's a really hot day.
Yeah, because this design was in Phoenix, Arizona. So, and you are trying to design for design day, right?
I see. Okay.
Yeah.
It's very interesting.
Right.
And then the last slide, also outside the building.
Yeah, this is outside the building. Another model and this one is the one which really, which led me to write that blog. The need to, use CFD to figure out some of these issues before they happen at the site.
So this is not a common practice for a designer to go and do CFD analysis to the standby generators.
It's not standard. It hasn't been standard. It's just we started doing it when we have a data center. In this case, we had a data center. We completed design of 84 megawatt, and we had over 52.5 engine, 2.5 megawatt engines. And if you think of each engine, air requirement is over 150,000 cubic feet per minute. With all those engines, we were looking at 7 million cubic feet per minute of air that is being moved. And that had a very big impact on the equipment which were located up on the roof. The air-cooled chillers were located up on the roof. And they were impacted by the hot air coming out from the engines. But with the CFD, we are able to correct this issue with doing different layout, and we still completed the design.
Okay, so one of the questions that during the blog piece that you wrote was asked was, okay, but you put in this one 120 degrees, the other one, I believe it was 115. How do you know the temperature? How do you know the wind speed and the wind flow direction?
Yeah, that was a very good question, actually, because where we get all the information on every project, it is the design requirement and the design conditions. And usually those conditions are governed by, they come from the client, and we will dictate either you have to use, and usually we use Ashley weather data. Ashley, they have a database of historical data of the temperature for every specific region, all over the world, I would say. And they'll provide us with, design condition for summer. I'll give a good example for Phoenix, Arizona, will be 110 degrees. They also provide you with other viable information, like the wind speed. The wind speed, average wind speed is this. The highest wind speed will be this number, and the lowest will be this number. And then as engineers, we look at that, and we determine, okay, what are we going to use? Which value do we need to use? And then we go from there. So the numbers, the wind speed, the temperatures, the densities, those are driven by the by the location,
right,
and as documented by the institutions like Ashley, Department of Energy, or not.
No, correct. Okay.
Yeah.
So, so to conclude, in a case like this or any other design case, the CFD analysis could you say that the CFD analysis could change the size or the amount of the equipment that you're installing and the configuration of it?
Like I mentioned, CFD does not replace the conventional way of doing the engineering, right?
Correct.
So the electrical engineers will size and come up with the number of generators they need to locate somewhere. The mechanical engineers will come with the number of the equipment they need. So what the CFD helps there is going in and validating the layout. Because initially, engineers will follow manufacturers' recommended minimum clearances between the equipment, and which is fine, and they will lay out the equipment like that. But then, when you have so many of them, you start wondering, will I have sufficient airflow, or do I need to take it to the next step, which is perform a CFD analysis for what we mentioned about visualization and understanding of more of the flow patterns that will be happening within your yard or within the data center.
So it could change the mechanical configuration to support the electrical equipment.
Yeah, definitely. And that's how we use it as a design tool.
So another question, I mean, I'm enjoying this conversation so much that I wish we could stay longer. Maybe another time we do another conversation like this. But before we move on, so we spoke about outside, we spoke about inside the data center, inside of the race floor area. Do you perform CFD analysis, for instance, if the CRA units are outside of the race floor area or in the battery room as well, for instance?
Yeah, if needed, yes. We'll do that too.
When you mean if needed, it's like, for example, when do you have to do a CFD analysis inside the data center, but not in the race floor area?
Inside the data center, but not in the race floor area. Yeah, we can do that to validate the layout. In this case, let's say you have a UPS room,
right?
And you have now I recently did one actually for a UPS room where the client wanted to reconfigure the ductwork. This was a system where there's no raise floor. They have crack units, which are upflow crack units, connected with one common header, and then out of that common header, this distribution ductwork that brings air in front of the UPSs. And it so happened that when the construction was done, the contractor flipped the UPSs. Some of them were facing away from where the ductwork and air supply diffusers were located. And that was having a very big impact for that UPS room because it was overheating. So to demonstrate that and to see what else can be done and configure the ductwork, we had to do a computational fluid dynamics and rotate everything. And you'll be surprised, instead of using 4 or 5 crack units, that reduced them to just use 3. So that's a huge energy savings there over time.
Now, if it was a new design, would you have recommended to relocate the UPS systems, and that would have saved to go and do a retrofit of that existing data center?
If it was a new design, they haven't built it, is rotate the UPS,
right?
To face the right direction.
I see.
What the contractor did.
Got
So I mean, in that case, what it was is it tells you there was no coordination between the mechanical contractor and electrical contractor, because this would have figured that before they put in the UPSs.
Or a CFD analysis would have figured that out before they start building this. Okay, this is really good. Gardson, thank you so much for your time. I really enjoy our conversation. Hopefully, we can do it, do another one like this one very soon. Thanks again.
Yeah, thank you, David, for having me. Talk to you soon.
Okay.
All right, thanks.